this video, I'm going to talk about Thomas iterative tetrahedron. So what is a Thomas iterative tetrahedron? Basically, we can define a Thomas iterative tetrahedron as a schematic framework that explain the complex relationship in the field of mechanical behavior of materials. Yeah. For example, we have here we have a characterization, we have a processing, we have a theory, and we have mechanical properties. All these and each one of these characterization, processing, theory, mechanical properties, all are interconnected to each other. Yeah. Now we move on to the example of a Thomas iterative tetrahedron. Here we have example of application of Thomas iterative tetrahedron in automotive industry. As you can see here in the diagram, this diagram shows the relationship between the performance and cost of materials in the context of automotive application. Yeah. For example, here we have the performance versus cost pyramid. What we can see here is that the previous diagram that I show you, it illustrates the balance between the cost performance in automotive materials influenced by the composition, microstructure, and manufacturing process. We can see here that in terms of performance versus cost pyramid, basically higher performance materials often cost more. And secondly, in a vehicle-related question, basically it addressed the material attributes like strength to density ratio, probability, the crash worthiness, and the fabrication cost. And in terms of a composition, it discussed whether a material is iron or aluminum based, and how the additional materials mix in for desired property. And in terms of a microstructure, it focuses on how the tiny structure in a material influence its strength and ability to be shaped. And in terms of synthesis and processing, here we explore the manufacturing process to achieve a desired material properties and aerodynamic design. Now we move on to the importance of material properties. The property of material is crucial to the application, and it can be applied to especially during the design specification. How can we estimate the formation and failure? And we can also relate it to microstructure to property, material selection, and also economic consideration. And now we are going to talk about the properties of materials. I think all of you know what is the definition of matter. Yeah, a matter is anything with mass that takes up space. We think of matter as a different materials or substances, and this material, it can form the object that we see, and it have unique features or properties. And our role as scientists and engineers, we study all these different types of material, we test their property, and we match property to the potential uses. Material property are features that we can see, features that we can measure or test. For example, here we have a certain type of material here. From the observation, we can see that it looks gray, maybe it looks hard and shiny, and based on a testing that we carried out in laboratory, the test revealed that it can conduct heat, electricity, and it reacts with acid. And testing shows that this material is able to conduct heat, and it will react with an acid. And in terms of matter, we have different types of stats of matter. The most common types are we have a solid, liquids, and gases, and the most less known stats of matter is what we call as a Bose-Einstein condensate. Yeah. And now we move on to the properties of material. As you can see in the table C, we have a different class of material property. For example, for physical property, we have a color, dimension, and shape, specific gravity, moisture content, micro and microstructure. In terms of chemical property, we have, for example, resistant to corrosion, a chemical composition. For psychochemical, we have dimensional changes with moisture changes. And for mechanical, a class of property, we have a strength, grip characteristics, stiffness, hardness and wear resistance, ductility. And for thermal, we have a melting point, coefficient of thermal expansion, specific heat. For electrical and magnetic, the typical properties are conductivity, we have galvanic action. In terms of acoustical, we have a sound reflection and transmission. And for optical, we have the typical properties such as the color, the light transmission, absorption, and reflection. And now in the table here, we can see different classes of property that affect the product design. We have actually seven parameters for grading material property. We have economic and environmental, we have a mechanical, we have a thermal, and here we have a general physical, and number 5 we have electrical and magnetic, number 6 we have environmental interaction, number 7 we have a production, and in number 8 here we have aesthetic. Yeah, so all these classes of property, they are very important for design consideration. So now let's take a look at the first classification of material property. We have economic and environmental. Yeah, and under this economic and environmental, we have a price and availability, recyclability, sustainability, and also a carbon emission. So for the first property here, we have a price and availability. It is very important for economic and environmental consideration. For example, materials that is too expensive, maybe it isn't suitable for mass production. For example, let's say we have let's say we have a diamond. As we know, diamond is very expensive. It is very strong. It has 90 to about 225 gigapascal strength. But is it practical if we want to fabricate a machinery from a diamond? Is it practical? Yeah, of course, it is not practical to fabricate machinery from diamond because it has a very high price and also limited availability. So what do? We find other alternative such as steel that is more cheaper and more available. Yeah, and then we take a look here at the second property under the classification of economic and environmental. Recyclability is the life and afterlife of a product. So when the product is of no use, what are we going to do with it? Yeah, and we have can you melt it and reshape it and give it another life. Yeah, and we have two. As you can see the figure here, we have two types of economy. We have a circular economy and we have a linear economy. So we take a look at first here. We have a circular economy. In the circular economy, it is where we use, return, we make, use, and return. Yeah. So in here, the companies, they view the materials as limited. They recycle and retain ownership of the material. On the other hand, in linear economy, it follows the take, make, and dispose model. For example, we have a light bulb production, disposal, and we assume in linear economy, we assume that we have infinite resources, which isn't sustainable. Yeah. And then here we have sustainability. We have a sustainability that focus on meeting the needs of the present without compromising the ability of future generation to meet their needs. And then we have a carbon emission here. We have a carbon emission. Before that, when we talk about sustainability, where we focus on meeting the needs of the present without compromising the ability of future generation to meet their needs in terms of economic, environmental, and social. And here we have a carbon footprint that can be defined as the total greenhouse gases from human activity. And it is measured in equivalent tons of carbon dioxide. So we don't want to develop a system that create too much greenhouse gases because it will cause harm to the environment. Yeah. All right. So now we move on to the third one, that is a thermal. And under the thermal classification, we have a thermal conductivity, specific heat, and also thermal expansion coefficient. So for thermal conductivity, it measures how well a material conducts heat. So it is a measure of its ability to conduct heat. For example, in a cool climate, if we compare between tile versus wood or carpet, which one is more colder to the step on in the cold weather? Yeah. Of course, if we compare tile versus wood or carpet, and we find that tile is more colder to step on a cool weather. Yeah. And then secondly, we have a thermal expansion coefficient. Before that, we take a look at the specific heat here. For specific heat, it is defined as the amount of heat per unit mass required to raise the temperature by 1 degree. For example, if we have a land versus water, which one absorb heat faster? We know that water heated up much slower at a much slower rate in comparison to the land, and as a result, we have environmental circulation that occurs. Yeah. And the third one, we have a thermal expansion coefficient. It measures how much a material expands when heated. It is caused by bonding forces and molecules, and the characteristic of thermal expansion coefficient, it varies between different types of material. For example, for soft metal, we have a high coefficient of thermal expansion, meaning that it will expand a lot when heated. And we have hard metals like tungsten that has a low coefficient of thermal expansion, meaning that it will expand less when heated. Yeah. So all We can say that a high CT material, it expands a lot or contracts a lot with temperature changes, and materials or metals with a low coefficient of thermal expansion, the material's size will change less with temperature. And now we move on to the next classification. We have a general physical. Under the general physical, we have a density that can be defined as the substance. The density of substance is its mass per unit volume. And then we have electrical and magnetic. And under electrical and magnetic, we have resistivity, dielectric constant, and we have magnetic permeability. Yeah. And if we look here, the resistivity of material can be defined as a property of material that quantify how strongly it resists or conduct electric current. And then we have a dielectric constant, and also we have a magnetic permeability that can be defined as the measure of the ability of material to support formation of a magnetic field within itself. Yeah, because we sometimes need materials to magnetize easily. For example, for in the application of electric motor, higher permeability materials equivalent to a better performance. And then we have environmental interaction, and under environmental interaction, we have oxidation, we have corrosion, and we have wear. We know that materials exposed to the environment can face oxidation and corrosion, and during use, materials also experience wear and tear. Yeah, and then under the class of production, here we have the ease of manufacturing, joining, and also finishing. These are the subclasses of production that will affect our selection of material.